Alright everybody, welcome to Calculus. This is the first calculus video I'm going to be making, and in this video I'm just going to we're just going to be doing some introductory calculus in this first video, but before that we need to go over some things that you're going to need to know if you're going to want to follow along this video. So calculus is all about breaking things down smaller and smaller and smaller with the derivative and putting things back together into bigger and bigger things called the integral. And so calculus is really split up into two different subsections. There's differential calculus and integral calculus. So, but before we get to integral calculus, because integral is a little bit more difficult, a little bit trickier, I'm going to get into some differential calculus. So, in your pre-calculus class, or even before that class, you learned how to find the slope of a line like this maybe. And you know that this line is of the form y equals mx plus b, or maybe ax plus b or something like that, where m is the slope here. So that's what you learned in previous classes and probably for the majority of your pre-calc class. And some of you, maybe at the end of your pre-calc class, touched on this newer topic, which is how do we find the slope of a line that's not linear? In other words, how do we find the slope of a parabola, for example? Or how do we find the slope of a cubic function? Or even, how do we find the slope of a quartic function that looks something like a w? Because look at this, a linear function like this, the slope is the same throughout. If we go to a parabola, it has different slopes at different spots. If we take this point right here, the slope looks something like this, right? Which is negative and fairly steep. If we take the slope of a point right here, we see that it's positive and not very steep at all. It's very gradual. So how do we find the slope of a function like this, or like this cubic function or this quartic function? And that's what the derivative of calculus is all about. And the derivative is something we're going to get to later, but right now we're going to be introducing the general idea of a derivative. So this problem of how do we find the slope of something that's not linear plagued mathematicians for the longest time. And it wasn't really until Isaac Newton and Gottfried Leibniz came up with the idea of the derivative that we solved this problem. And their solution to this problem was, let's say you have this parabola right here, and I want to know the slope at this point. So I can basically, or let me pick another point actually. Let's say I want to know the slope of this point right here. I can place another point right here and draw what's called a secant line. And if this is a graph right here like this is our y-axis and this is our x-axis. Here we have x, and here we have like another x, I'll call this x2. And the distance in between them is, let's call it h. And now, the secant line represents the average rate of change. I can't find the slope at this point exactly, but I can find how much this graph is changing on average with the secant line. Well, let's say I did that again, but with a different point that was closer to the original one. Now it looks something like this, right? And now our x2 is somewhere over here, and our h is even smaller. And you can see I can keep doing this. I can keep creating more points until I get so close to the original point that it really doesn't even matter. The distance between them is negligible. Let's say our x value is 2, and I make my x2 value 2.000000000, 10 more zeros, and then 1, right? That difference is so small, it's almost negligible. So they came up with the idea of the limit as h approaches 0 in other words, the limit as the distance between the 2 points gets closer and closer to 0 of f of x plus h. And remember, x plus h would get you to x2, right? X plus h minus f of x over h. And that's the limit definition of the derivative. And that's something we're going to get to later, but for now I really want to focus on the secant line and the average rate of change. So in order to find the average rate of change, which I'm going to abbreviate as AROC, or something you might see it also as is M secant, like this. This just means slope of the secant line, because the slope of the secant line would be your average rate of change, is f of b minus f of a over b minus a. And your a and your b in this case, it would be on an interval like between x and x2. Like on an interval, a to b is the same thing as saying on an interval x to x2. And this is essentially just the slope formula. If you really think about it, f of b is going to be some y value. Let's say like this. F of b is like that. And f of a is going to be another y value. And then b minus a are these x2 and x values. So really what this is just y2 minus y1 over x2 minus x1. And that's going to give us the average rate of change. Okay, so in this next question, or in this first question rather, we are told that a tank holds 1,000 gallons of water, which drains from the bottom of the tank in half an hour. The values in the table below show the volume V of water remaining in the tank in gallons after t minutes. And this is a two-part question. In the first part, they say that if P is the point 15 to 50 on the graph of V, find the slopes of the secant lines PQ when Q is the point on the graph with T equals 5, 10, 20, 25, and 30. So really in this first part we're going to be finding the average rate of change at 5 different points. So it's really like six questions, 5 in part A and 1 in part B. And in part B we have to estimate the slope of the tangent line at P by averaging the slopes of the two secant lines. So I alluded to this just a couple seconds earlier, but for this first question we're going to be finding the average rate of change, or the slope of the secant line. And if you can't recognize why, here's why. They give us a point P, which has it has an A value and an F of A value. And then now they're telling us to find the average rate of change along all these different B values. So like 5, for example, is a B value, 10 is a B value, and so on and so forth. And we can see that each of these B values has an F of B value, which is the amount remaining in gallons. So for part A, what I'm going to do, I'm going to go to this new screen over here, and I'm going to do if I'm going to write the interval as 15 to 5. So really we're going backwards on this interval. But that's perfectly fine. So I'm going to write down the formula. M secant is equal to F of B minus F of A over B minus A. And our F of B in this case is going to be our F of 5, and our f of 5 is 694. So I'm going to have 694. Let me write this better. 694 minus 250. And then our b and a values are just this right here. So our b value is going to be 5 minus 15. So I don't know what 694 minus 250 is off the top of my head, so I'm going to get out my calculator and do that. So feel free, if you have a calculator near you, to go ahead and do that. So 694 minus 250 is 444, and 5 minus 15 is negative 10. So this is pretty much as simplified as you can get it, or I guess you could divide both the numerator and the denominator by 2. So 444 divided by 2 is going to be 222. So we're going to have negative 222, and then 10 divided by 2 is 5. So negative 222 over 5. And this number does make sense for the average rate of change, because if you think about it, we're basically going backwards here. We're going backwards on a graph, so it's going to be negative. Then on the interval of 15 to 10, which is what it asked us to do next, so I'm going to write on the interval of 15 to 10, I'm not going to write the f of b minus f of a because we already know the formula, and if you need to see it, you can just rewind a couple of seconds. So our f of b, our f of 10 is going to be 444 minus our f of 15, which is 250. So 444 minus 250 over 10 minus 15. And before we even solve this, I know it's going to be negative because we're going backwards on the graph again. So I know it's going to be negative that way, and 10 minus 15 is obviously going to be negative 5. So once again, I don't know how to do 444 minus 250 in my head, so I'm just going to do that on a calculator, and it's going to be 194 over negative 5. So that's going to be our answer for that interval. And then our next one is going to be on the interval 15 to 20. So I'm going to do f of 20, which is 111, minus 250 over 20 minus 15. And now this is going to be negative still, but for a different reason. The reason it was negative in the previous two intervals was because we were going backwards on the graph. Now it's negative just because it's this is a negative function. The volume of the tank is going to be decreasing if water is draining. It's just going to be negative. So I'm going to have to do 111 minus 250, which is negative 139. Negative 139 over 5. And that's going to be our answer for that one. And then I have on the interval 15 to 25. So f of 25 is going to be 28. 28 minus 250 over 25 minus 15. So 28 minus 250 is going to be negative 222 over 10. And we can divide the numerator and the denominator by 2. So 222 divided by 2 is just going to be 111. So we have negative 111 over 5. So that's our answer for that one. And then we're finally going to do the interval 15 to 30. So f of 30 is 0 minus 250 over 30 minus 15. And that's going to be negative 250 over 15. And we can divide both the numerator and the denominator by 5. So 250 divided by 5 is going to be 125. It's going to be 50. So we're going to have negative 50 over, and then 15 divided by 5 is 3. So 50 over 3, and I believe that's as simplified as we can get it. So negative 50 over 3 is going to be our final answer for that one. And remember, I know we did this kind of quickly, but it's important to see what you're doing in all these problems. We're finding the average rate of change. So on average, let's say between the interval 15 and 30, on average, the tank was draining at the tank was losing 50 over 3 gallons per minute. So that's what we were doing in that one. And for part B, it says estimate the slope of the tangent line at P by averaging the slopes of two secant lines. I didn't really go over the tangent line in the intro video, so I'm going to do a more thorough explanation of that now. If I have a parabolic function like this, the tangent line is a line that just barely skims the function. It just touches the function at one point and one point only. So like that. I can even draw that better if I wanted to, so I can do like this. And this is what's called the instantaneous rate of change. It's how something is changing at an instant rather than the average rate of change. And so this is what I was talking about. This is what the derivative is going to allow us to do. But we can do that using secant lines by averaging the slopes of two secant lines that are near that one. So it wants us to estimate the slope of the tangent line at P by averaging the slopes of two secant lines, and P is 15 to 50. So we can add the slope of the secant line that we got on this interval and on this interval, and then divide them by 2. So I don't remember exactly what we got for these intervals because I did them on a calculator and then I erased them, but you should just be able to pause the video, go back, and fill those out for yourself, and you should get the right answer. So that's how you do that one.